Right, so today we're talking about Dependency Hell and the absolution from it. And Nick's obviously trying to be a path to solve that problem. So when we talk about Dependency Hell, we're basically summing it up by saying when people stop valuing simplicity over complexity. Barbara does that beautifully. If you like complexity over simplicity, it's probably not the right room to be in right now, but just stay along and listen anyway. So we've got 7 definitions of hell. Hell is a situation where dependencies are greater than the actual application that you're building. Classic example here, and all the code samples in here are based on Node for a reason that will become apparent later. But npm install save Gatsby. If we see, we've done some package installs and we've added 19,000 dependencies. It's a little bit more than you were hoping to do with just installing one thing. Maybe it's necessary, maybe it's not, but if there's a problem, it's really hard to figure it out. Hell is long chain dependencies and conflicting dependencies. So we've got program A depends on program B, depends on program C, one version depends on program D, etc., 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 etc. Program E depends on B, depends on C, etc., etc. And then along comes program Z, which depends on B, and suddenly depends on a different version of C, and then depends on something else. At this point, your globally installed package goes, I actually don't know which one you want because C version 1 and C version 2 are different, but they're also the same program. So how do I resolve this? And as I'm not smart enough as a package manager, it's over to the user who has probably never seen this before and goes, I don't understand. Hell is circular dependencies. This is actually a perfect software solution example of what we do commonly. A depends on B, which depends on A. And this actually happens in package managers, where the package manager depends on a library that's used to build the package manager, and then the package manager is asked to update that library, which it updates and then can't update itself, and sort of just sits there in a loop where it goes, I have no idea what to do. And at this point, usually the system just starts falling apart. Hell is also diamond dependencies. So say yum depends on program B, depends on D2, and program C depends on D1. Well, they're both depending on D, but we're at a diamond because we don't know which version of D and how do we install and manage both versions of D. So we kind of solve dependency hell, or have to date, by using package managers. And it's in the name. We think that managers of packages would be very effective at what they do. But we kind of get the situation, which I'm just calling yummed because this happens often with yum, where you do something like yum install meetup, error, meetup conflicts with Zoom. It shouldn't, but it does. What does the user do at this point? Because that's an ambiguous error message. So we try to solve via the package manager. We try and solve what the first problem of cycles via bootstrapping. So we create an operating system, which is where all of your operating system flavors like Debian, Ubuntu, and all these forks all the way down, there's hundreds of them now, thousands of them now, where it's a minimal system with a few cyclical packages. So all the cyclical dependencies, we say bundle them up together, release them as one piece, and then everything hopefully should just depend off these. And if something does really depend on a different version of that, just wait till the next release, where you load a temporary file system, swap out your cyclical dependencies, and then come back and hope it all holds together, which is where you get that major every so many months you need to install a brand new operating system. It is capable of providing dependencies for other packages, and it does make the system harder to backdoor as everything is pinned. Gentoo is the perfect example of this. And for whether you've used Gentoo or not, it's probably a good time to stay awake at night and have a try. The other way we solve the problems with package managers, or package managers try to solve dependency hell, is where there's conflicts, they'll provide an alternative. So VI and Vim is a perfect example. Most package managers do this. They are physically different programs. VI and Vim are not the same program. They're not even written by the same author, but they're allies to a common expectation where people type VI and they expect Vim to appear. So this conflict, just provide an alternative, should take care of itself. We can also solve via atomicity and transactionality. The problem is this is not available in what we call legacy systems. So anything like Windows, Debian, RHEL, or any of those different branches don't have an ability to manage atomicity or transactionality because of the way they're built. We can also solve with system rollback or versioning, but again, you need transactionality to implement these. And if it is implemented, your state of your system would just become version snapshots, which sounds pretty easy. Your package manager then just becomes a transition function between snapshots instead of this massive cyclical, non-cyclical conflict resolving machine. And where does this problem come from? Dependency Hell itself is actually pretty old. It came through with the introduction of the file system hierarchy standard, or FSS, which came as part of Linux. It's fundamentally incompatible with reproducibility. The reason being that when you type your address and you go //, you have no concept of what software version you're using. You've got no concept of what libraries that software requires to use or depends on. You've got no concept of whether this was optimized for a hardened build, a non-hardened build, whether it's optimized for your architecture or it's a generic type of build. Nothing. And you just trust that that current piece of software that's installed will work forever. And when it's upgraded, it will happily upgrade without breaking anything. And the reason we have package managers is because that's not the case. The other thing that happens is we have a challenge between author and maintainer control. If the author controls the package definitions or the upgrade definitions or even the build definitions, then typically things are more up to date. But they tend to wander in terms of standards and readability because, as all software developers, over time your software gets better and you find better ways of doing things, which may conflict with standards because it's just you developing in isolation. The other thing that happens is you have to go to the author's repositories and collect all the pieces, and people don't generally want to go to one place to collect things to install operating systems. They don't want to wander around 200 plus repositories to pull them all together and then keep discovering them. If we do a maintainer type of control, typically things are more stable, but we've also got rigor. As with some packages, you can also add linting because you're building standards, so there's best practices and ways of doing things. But you don't get that flexibility you have with an author. So there is this tug-of-war challenge. And then what if something has changed fundamentally and you need to patch that? You now have to go through the change control process. Someone has to approve it, validate it, and that can take a long time when something's broken. So we also introduced the concept of binary blobs. And binary blobs in terms of package management is a valid option that was presented. Things like app stores, OCI containers, Snap, Flatpak, App Image, and there are others that still fall into the binary blob type of category. All of them do the same thing. They ignore most of the issues that we have come across with package managers and literally pretend they don't exist. Their process is to isolate the file hierarchy system, and all will be well because my dependencies shouldn't double depend on something. Maybe. If you've gone through the process of building any of those, you will find that with every single one, you can get multiple variations of builds. You can get builds that break. And then you dig into this nice little archive of how do I actually build and manage packages and dependencies without getting into dependency hell. We have discovered over many years of developing software that languages are superior. Partly because they allow loose versioning. So you can do, if you're following the Semver standard, caret 1.0.0, and if you're pretty good for just building on most places, you can always pull in the latest code by doing that. You are unable, though, to manage other languages. So now if you want to manage packages, every language needs to have its own package manager. And if you're programming in multiple languages, like we do in C and CF kind of situations, then you need to manage and look after each of those and become an expert in all of them, or use teams that are experts in those languages. They can vary in quality depending on the languages, and the language must support pinning or exact versioning. Otherwise, when you build on a production system, it may be different because it was just built 24 hours later than building in a development version because someone released a patch somewhere, which can potentially break your code. npm CI supports pinning, and pip install plus pip tools also supports a kind of pinning approach. So if you're using either of those two, you've got a way of doing it. When we talk about the language dependency chain and how it resolves, your typical situation is this kind of situation where A depends on B, depends on C, but A also depends on C version 2. C version 2 depends on D. D depends on C, another version 3. Also depends on library B version 2. C3 may depend on D2. B2 may depend on C4. And D2 may depend on B. Who the hell knows at this point? Because you've just got this massive chain of dependencies, which your software now needs to be smart enough to resolve to a single shared dependency that can be bundled into your final build. And that's really the complexity of what your language managers are trying to solve, and why they're so much more typically powerful than a standard package management system in a Linux type of environment. We look at npm build, which is your standard package manager in Node. It has 649 dependencies that are necessary to build itself. It's actually needed to build and manage itself. It can be a package manager for an operating system, and there is actually an operating system called Node OS that runs npm and runs a full system based on it. So it's a very powerful package manager, which is why it's here versus other package managers and languages. But it does need itself to build itself. This is the visual representation of npm's dependencies, all 649 of them, and how they interlink and depend on each other. I know it's not readable, but it's there to give you an idea at a very high bird's eye view. You can start to see the lines all circling around each other, and you can start to see the common packages here. Presenting an alternative Nix build, it has 34 dependencies. Any system with glibc can build and run Nix. In terms of a dependency graph, that's the entire dependency graph coming all the way up to libunistring as an OSC library. Nix building npm has 25 dependencies. It's a little bit of a variation from the 649. It has one extra dependency than would be required to actually build and run Node.js itself. And this is the Nix dependency tree for npm. Just draw your attention to up here. You can see we've got Node.js as one of the dependencies for Node npm. So that's the one extra step. We take that away, and all of a sudden we've got Node.js working versus Node npm working. So Nix, in what we've seen so far, can be the future of computing if we can find a way to actually explain Nix. Nix has a concept of a store. The concept of a store in Nix is designed to fix the file hierarchy system problems. And it was addressed in a paper that was published to basically go against all the criticism people placed around Linux, and that's where Nix evolved from. It uses a directed acrylic graph via the file system. The directed acrylic graph and store is actually a database and queries as such. So you can literally run Nix store query, references Nix/store, and then go to what is the current build of Nix on my system, and you will get the result of all the dependencies that Nix actually needs, all the number of them, to produce Nix itself. And you can do that on any machine. So you can literally copy the entire Nix store directory to any machine within the same architecture class, and it will be 100% reproducible, 100% exactly what you need to be. You don't need to worry about it. So you've got built-in caching, built-in immutability, lots of good things you don't generally have in Dependency Hell. Nix is also a hash-based system. So that hash we saw previously above links to a derivation. And the derivation, if we pull it apart, expands to this long piece of code, which builds and maintains the actual hash expression. So if we change any dependency at all, be it a version, be it a path, be it a architecture, it will change the hash and we will have a brand new version built. You can see more detail on this in Nix pill number 18. If we're to explain Nix simply, then Nix is like maintaining or upgrading a car. Debian and all the other variations feel like working on your own car in your own garage. The results may vary, especially if you're in IT. Nix, on the other hand, is like 3D printing a brand new car every time you change something. You don't worry about the old one, just build a new one. If you got the headlight wrong, just build a new car. Nix is a turning complete language. So the machine can understand the machine in terms of configuration, in terms of building, and in terms of runtime of your application. Nix provides reproducibility on any machine. So it doesn't matter if you're developing, it doesn't matter if you're running in CI, it doesn't matter if you're running in CD. Every single machine will be reproducible exactly. You've got autonomicity and transactionality built into Nix. You've got binary caching available, so you can check your caches because you know the hash, and you don't need to rebuild what hasn't changed. That can be pushed to S3, that can be maintained on disk, or there is a Nix service called Keidrych, which will do that effectively too. It's normal to have multiple packet versions within Nix, as opposed to other systems where they're the outlier and you need to resolve the dependency. You can happily live with them in Nix, nothing conflicts. It will do distributed builds. So if you have very long, complex pieces of build, you can run them across multiple machines, bundle them all up, and deliver the final package. And you run non-privileged builds, so it doesn't need privileged access to do any building. It also has integrated secrets management via SOPs, and this is the Mozilla SOPs library. So it's actually safe to put secrets in Nix that you need to use and have that published in an open source repository, which I think is pretty dang cool. So if we try again, we can explain Nix as a language that produces a .drb file into a store, which does bundling and executing via a sandbox, assembling part or all of an operating system via Nix. Some or all of this functionality can be used at any point in time. If we're to install Nix on any OS compatible machine, so like a Linux system, a BSD system, so you can install it on your Apple Mac, you can install it on any flavor of Linux, you can install it on Unix if you really wanted to. You just need to run curl, install shell, the shell script will take care of it, so it is a relatively easy system to install. We're to do a hello world because every good presentation does hello world. Then you can see here we can import the Nix package library. You can import that, you can extend that, you can customize it, you can find your sources of a group community. You can have an internal one within your own company if you wanted to maintain, because everything is just a Nix expression as a language. And then we go ahead in this case and we say, right, give me a shell script. And the shell script should be called hello world, and it should just echo hello world. So we're going to make the derivation. We're actually going to build the package. We're going to call it test environment, and we're going to add it to the path. To build that, we just go Nix shell hello world. And now we have a completely sandboxed environment which has built and is able to run hello world according to our expression. If we have a look at that derivation, you can see that the derivation itself is not that dissimilar to the other one we looked at earlier. We're making the directory, we're handling how it all builds. It has done a little bit of language-specific and package-specific management in there, but that's part of the Nix packages expression to make it simple for us to use the derivations. We can go to Nix store and we can query it as a directed acrylic graph. You can show me all the upstream references for my now built hello world package. And we can see that it depends only on bash, as we would expect, only the shell, and whatever the shell dependencies are, we could go through and build the graph like you saw previously. What if we wanted to do something more complex? What if we wanted to use curl and use JQ to reach out to a website, go and fetch something, and then pull it down? Well, in Nix, that's pretty easy because you go ahead and you import your Nix packages again. And then you go ahead and you just write your shell script like we did previously. This one is a what is my IP shell script. And we just go $packages.curl. So this will now inherit the curl package and all of its dependencies to run just this command. And it will inherit the packages.jq and all of its dependencies to just run this command. Finally, if you wanted to go into a really powerful example of what you can do with Nix, you can have a look at the Containizen project, which I did a demonstration on previously. It's entirely built and maintained using Nix. It also builds all of the OCI containers via Nix to standardize them and make them identical.